all to this VLSI series of lectures. Today I am going to discuss about the internal block description of CPLD. I am Seshagiri Rao, Associate Professor in Electronics and Communication Engineering Department. So the instructional objectives of today's class are: define what is a complex programmable logic device and list and explain the principle of operation, the various functional units within the CPLD. So, with the advancement of technology, it has become possible to produce devices with higher capacities. And as the chip densities increased, it was natural for PLD manufacturers to bring products with larger parts, so which can realize bigger Boolean functions. So these are called as complex programmable logic devices. So for most practical purposes, the CPLD can be thought of as multiple PLDs which are interconnected through a switching matrix. So the larger size of CPLD allows to implement more logic with more variables for a complex design. Now this is the internal structure of CPLD. So here you have the logic block, this is a logic block, and this is another logic block, and this is another logic block. These logic blocks are connected through the switch matrix. But in actual CPLD, there may be more logic blocks, more than these 4 logic blocks. They contain 70 or 90 or 100 depending upon the part number of the manufacturer. So these logic blocks are themselves, they comprise macro cells and interconnect wiring just like any ordinary PLD. Now I'll give you the generic architecture of the CPLD. So just now we discussed that the CPLD contains PAL-like blocks or PLDs. What is PAL? PAL is programmable underplane and fixed arc plane. So this is a generic structure of CPLD. This is a PAL-like block. And let us say this is also another PAL-like block. So I'll simply write PAL, and this is another PAL, and this is another PAL. And these paths are connected to external environment through the IO pins. So we have the IO blocks. This is one IO block, and this is another IO block. Here also I have IO block, and this is another IO block. And these poles are connected through this to the external environment through this IO pins. Some are input pins and some are output pins, and some may be input output pins also. So these are the connections between the PAL and the IO blocks. So here also I have the connection between PAL and IO block. So this is IO block. This is also IO block. IO block. And these poles are interconnected with each other by a switching matrix. So that means the output of one pole may be the input to another pole. But how the connection is done? Through a interconnection wires or a switch matrix. So this is the interconnection wires. So like there is a connection between the pole and this block, interconnection block. And these interconnection wires are also connected to I/O blocks. And the signal can be in both directions. So this is the structure of CPLD. And a PLD contains macro cells. And the macro cell structure is like this. It can have a programmable interplane, and the AND gates, the programmable AND gates are connected to OR gates to form SOPs. SOP is sum of products, and these in turn they are connected to a flip flop. So whenever you have a flip flop, there is a facility to go for sequential design. So the typical structure of macro cell is like this. I have AND gates which are programmable, and these are connected to a set of input signals, input lines like this, and these are programmable. And you have an OR gate. Through OR gate, you can form a sum of products Boolean function, and this is the D flip flop. And the output of this is given to the D flip flop, and this is the output from the flip flop. And here I have a multiplexer. So the output of the flip flop is given to the multiplexer, and I can as well directly give the output of OR gate to the flip flop to the multiplexer. This is 0, 1, and it has one select line, and this is given to the enable buffer. So you have a tri-state facility enable. If the signal, if enable signal is not there, then the output is tri-stated. So here I get the function F1. Okay. Now F1 and in most of the macro cells, exclusive OR gate also is kept. So this is an exclusive OR gate, and one input is F1 and another input can be 0 or 1, and this is you can get, if you give the input 1, then you will get F1 bar. If input to the exclusive OR gate is 1, we get F1 bar. Otherwise, if input is 0, then we get F1. So that is an advantage of having the exclusive OR gate in the macro cell. Of course, I will demonstrate this with an example later. So this is a D flip flop, so it has a clock. So this is the typical structure of a macro cell. So each PLA contains number of such macro cells. So this macro cell, it facilitates the design of combinational as well as sequential functions. So unlike the programmable interconnect within a PLD, in CPLD we use a switch matrix, and using the switch matrix, the poles in CPLD are interconnected. But it is not necessary that all poles are connected. Every pole is connected to another pole. So you may not have full connection, but you have the required number of connections so that you can implement the Boolean functions. So in other words, some theoretically possible connections between logic block outputs and inputs may not actually be supported in the CPLD. So what is the effect of this? 100% connection of macro cells is not possible. So because of that, some hardware designs may not fit in the given CPLD. Even if there are sufficient poles and even if there are sufficient flip-flops. So CPLDs are exactly what they claim to be. There is a difference. Before CPLD we had SPLD. SPLD is simple programmable logic device which had only limited number of poles and only Boolean functions with small number of variables were able to be realized. But in complex programmable logic array, you can design Boolean functions with hundreds of variables. So these are designed to appear like a large number of poles in a single chip, and they are connected through a cross point switch. And these CPLDs, they use same development tools and they use same programmers, and they are based on the same technologies like SPLDs, but they can handle much more complex logic and more of it. So CPLD is a programmable logic device, and with complexity between poles and FPGAs. In previous session, we discussed about the field programmable logic array, and the complexity of the CPLD is between the POL and FPGA. And it has architectural features of both. So the basic building block of CPLD is the POL, whereas the basic building block of FPGA is lookup tables. Now let us discuss what are the common features of CPLDs with POLs. POL is programmable array logic, which has programmable end-plane and fixed R-plane. So the features which is common with POL is it has non-volatile configuration memory. So unlike FPGAs, where the programming environment is outside FPGA, that means the programming data or the bitstream data is stored outside FPGA in SPROM, and every time you power on, the bitstream is taken into FPGA and FPGA gets configured. And the moment you switch off power, FPGA becomes blank. But CPLD, the programming is inside, so in a non-volatile configuration. So here we don't require ROM, but CPLD, it can function immediately after the system is powered on because it has the built-in non-volatile storage. And for many legacy CPLD devices, routing constraints or routing limits most logic blocks to have input-output signals connected to external pins, reducing the opportunity for internal data storage and deeply layered logic. So this is usually it is not a factor for other CPLDs. Now let us see what are the features which are common with FPGAs. What is the commonality between CPLD and FPGA? Let us discuss. And after that, I am going to discuss about the differences between CPLD and FPGA. So, as a large number of gates are available, CPLDs they have the equivalent of thousands to 10,000s of logic gates. So, you can implement moderately complicated Boolean functions. But PALs have only few hundred gates, whereas CPLD you can have up to tens of thousands of logic gates. So you can implement moderately complicated Boolean functions. But in FPGAs, you have millions of gates, so you can implement even more complicated data processing operations. So some provisions for logic are more flexible than some of product expressions, including complicated feedback paths between macro cells and specialized logic for implementing various commonly used functions such as integer arithmetic. So these are all the features which are common with FPGAs. So I have shown you the architecture of CPLD. Now it has the PALs, and while each manufacturer has a different variation, that means depending upon the part number, you may have a different number of PALs or different number of macro cells. Some CPLDs may have 15 PALs, and in each PAL, the number of macro cells which it contains may differ. So, while each manufacturer has a different variation, in general, they are all similar in that they consist of functional blocks and input-output blocks and interconnect matrix. And these devices are programmed using programming elements and depending upon the technology of the manufacturer. So the programming technology may be EEPROM or electrically erasable PROM or flash EEPROM cells. So the basic block of CPLD is PAL. PAL, it has the programmable underplane. So underplane still exists, and it is shown by, I have shown you by the crossed wires. And the underplane, it accepts inputs from the IO blocks and other functional units and feedback from the same function block. So these terms are ORed using a fixed number of OR gates, and these are selected using a large multiplexer. So as I have shown you here, this is a programmable underplane, and this is an OR gate, and you have a multiplexer. So I'm talking about all these things now. And it also, the outputs of the mux can be sent straight out of the block, or it can be sent to a clock flip-flop in case you are implementing a sequential logic. And you also can have an exclusive OR gate which gives the function or the complement of the function. And IO blocks. IO blocks, they are used to drive the signals to the pins of CPLD at appropriate voltage levels with appropriate current specifications. So usually a flip-flop is included. Interconnect. Interconnect is used to connect the internal PALs within the CPLD. So the CPLD interconnect is a very large programmable switch matrix that allows signals from all parts of the device to go to all other parts of the device. But of course, just now we discussed that full 100% interconnection may not be, it is not possible. So each PAL is not connected to all other PALs. There is a limitation. So while no switch can connect all internal function blocks to all other function blocks, there is enough flexibility to allow many combinations of connections. Now let us come to the programmable elements. Programming is required because each CPLD may be used to implement different Boolean functions. And during design stage, that when the design goes a number of iterations, you may have to make some corrections in the Boolean functions, so you can readily do it by appropriately programming the flash memory or EEPROM. So different manufacturers, they use different technologies to implement the programming elements of CPLD, and the common technologies are electrically programmable read-only memory and electrically erasable PROM and flash EEPROM. So these are similar to the next generations of the technologies that were used for the simple programmable devices PROMs. Now let us discuss about the architectural issues. So when you have decided to use a CPLD for your design, how to select the CPLD from the market or from various manufacturers? So what are the factors that are to be considered? What are the factors you have to take into account? So these are, first is the programming technology. So you have to see whether it is EEPROM or EEPROM or flash EEPROM, because this determines the equipment you have to procure, and also you have to consider whether programming, how many times you can do the programming. Okay, so these are the two aspects of the programming technology. So one is the equipment needed to program the devices, and another is how many times you can do the program. Next architectural issue is the function block capability. How many function blocks are there in the device? That means how many parts are there, and how many product and subterms you can use. What is the limitation on that? And what is a minimum and a maximum delays through the logic? Is it as per your requirement? Is it as per the performance specification? And what additional logic resources are there, such as XOR gates, XNOR gates, and ALUs. So you have to see all these additional logic resources which are included in the CPLD, and what kind of register controls are available. For example, clock enable, reset, preset, and polarity control. And how many are local inputs to the function block, and how many are global and chip-wide inputs. The inputs may be within the CPLD, or some inputs may come from the outside to the CPLD, and how many are global and how many are chip-wide inputs. Global means, see, the clock what you use, it is a global, and how many are chip-wide inputs. So all these things you have to consider. And the next point what we have to take into account is what kind of clock drivers are there in the device, and what is the worst skew of the clock signal in the chip, because this determines the maximum frequency at which the device can run. Next aspect is the input-output capability, and how many input pins are there, how many output pins are there, because how you have to see how many devices you can connect. So, and how many are dedicated for clock input, master, reset, etc. And another aspect is what is the output drive capability in terms of voltage levels and currents. This is aspect also is to be examined before you select any CPLD for the specific application. And what kind of logic is included in an IO block that can be used to increase the functionality of the design. Now, let us have the comparison between the FPGA and CPLD. What is FPGA? Field Programmable Gate Array, and CPLD is Complex Programmable Logic Device. So the most noticeable difference between CPLD and FPGA is presence of non-volatile memory in the CPLD, And this makes the CPLD an obvious choice to perform booting operations. Okay. So what is the example is the CPLD. It is used to load the configuration data for an FPGA from non-volatile memory. And in the case of FPGA, we have seen that you use SPROM outside the FPGA for programming, whereas in CPLD the programming is inside the CPLD itself. So the main distinction between FPGA and CPLD architectures is FPGAs use lookup tables, while CPLDs use programmable array logic devices with the C of gates or sum of products. So the CPLD, it contains Paul-like structures, and the Paul-like structures are programmable logic devices, and for example, this can be used to implement different Boolean functions. Now let us take an example of PLA to realize a Boolean function. Now let us say here this PLS 100 has 16 inputs and 48 AND gates and 8 OR gates, 8 exclusive OR gates, as you see here. So here I0 and I15, these are the 16 inputs, and here you have 48 AND gates, P0, P1 and P47, and 8 OR gates. These are the OR gates 1, 2 and this is 8, and exclusive OR gates also you have 8. And what is the use of exclusive OR gate? You can realize the function F1 or F1 complement by simply making the other input 0 or 1. If the other input is 1, you get the complement, otherwise you get the same function itself. Now let us take this example. F1 is equal to 2457 and F2 is equal to 01246. As the maximum number is 7, 3 variables are sufficient. So here I have taken A, B, and this is C, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1. So here 0, 1, 2, 3, 4, 5, 6, 7. You have 2, 4, 5, 7. So 2, 4, 5, 7. So you can do the minimization like this, and this is another minimization, and this is alone. So you get the function like F1 is equal to AB bar plus AC plus A bar BC bar. So this is F1, right? Now F2 contains 0, 1, 2, 4, 6. So you have taken, this is 0, 1, 2, 4, 6. So you have more number of ones here. So instead of pairing ones, if you pair zeros, then you can obtain the Boolean function with minimum number of variables. So what you can do, you can pair this and you can pair this. But when you pair zeros, you get complement of the Boolean function. So you get F2 bar equal to BC plus AC. Okay. So you see here I am getting F2 bar. How I am getting? This is BC and this is AC and this, okay. And here I am getting F2 bar and this I am giving it to the exclusive OR gate and I am making the input of exclusive OR gate as 1. So this is 1 I am making. So I get directly here F2. And here F1. F1 is AB bar, AC and A bar BC. So I made connections and I am getting here directly. Because I have to get the function directly, here I should give the input as 0. So I am giving input as 0 and this is F1 and I am directly getting F1. So if you include exclusive OR gate, we can get the same function or complement of the same function. So we have discussed about the CPLD. The basic differences between CPLD and FPGA is FPGA, the Boolean function realization is done using the lookup tables. In CPLD, the PLDs are used, mostly the PALs, which have the programmable and plain. And the programming environment is within the CPLD, but in FPGA, the programming environment is outside. And the complexity or the number of gates is more in FPGA, whereas the number of gates is medium in CPLD. And the power consumption is likely to be more in FPGA compared to CPLD. So with this, I conclude today's session on CPLD. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.